1 and okay. Here is a lecture on the applications of eigenvalues, and if I can, so that will be Markov matrices. I'll tell you what a Markov matrix is. So this matrix A will be a Markov matrix, and I'll explain how they come in applications. And then if I have time, I would like to say a little bit about Fourier series, which is a fantastic application of the projection chapter. Okay, what's a Markov matrix? Can I just write down a typical Markov matrix, say 0.1, 0.2, 0.7, 0.01, 0.990, let's say, 0.3, 0.3, 0.4. Okay, there's a totally just invented Markov matrix. What makes it a Markov matrix? Two properties that this matrix has. So two properties are, one, every entry is greater or equal 0. All entries greater than or equal to 0. And of course, when I square the matrix, the entries will still be greater or equal 0. I'm going to be interested in the powers of this matrix. And this property, of course, is going to stay there. Really, Markov matrices, you'll see, are connected to probability ideas, and probabilities are never negative. The other property, do you see the other property in there? If I add down the columns, what answer do I get? 1. So all columns add to 1. All columns add to 1. And actually, when I square the matrix, that will be true again. So that the powers of my matrix are all Markov matrices, and I'm interested in always the eigenvalues and the eigenvectors. And this question of steady state will come up. You remember we had steady state for differential equations last time? What was the steady state? What was the eigenvalue? What was the eigenvalue in the differential equation case that led to a steady state? It was lambda equals 0. You remember that we did an example, and one of the eigenvalues was lambda equals 0. And so then we had an e to the 0t, a constant, 1. As time went on, there that thing stayed steady. Now, what in the powers case, it's not a 0 eigenvalue. Actually, with powers of a matrix, a 0 eigenvalue, that part is going to die right away. It's an eigenvalue of 1. That's all important. So this steady state will be totally connected with an eigenvalue of 1 and its eigenvector. In fact, the steady state will be the eigenvector for that eigenvalue. Okay, so that's what's coming. Now, for some reason, then, that we have to see, this matrix has an eigenvalue of 1. This property that the columns all add to 1, turns out, guarantees that 1 is an eigenvalue. So that you can actually find that eigenvalue of a Markov matrix without computing any determinants of A minus lambda I. That matrix will have an eigenvalue of 1, and we want to see why. And then the other thing is, so the key points, let me write these underneath. The key points are lambda equal 1 is an eigenvalue. I'll add in an additional, well, thinking about eigenvalues, key point 2, the other eigenvalues, all other eigenvalues are in magnitude smaller than 1, in absolute value smaller than 1. Well, there could be some exceptional case when another eigenvalue might have magnitude equal 1. It never has an eigenvalue larger than 1. So these two facts, somehow linear algebra ought to tell us. And then, of course, linear algebra is going to tell us what happens if you remember when I solve, when I multiply by a time after time, the kth thing is a to the k u naught. And I'm asking what's special about these powers of a. And very likely the quiz will have a problem to compute some powers of a, or applied to an initial vector. So you remember the general form? The general form is that there's some amount of the first eigenvalue to the kth power times the first eigenvector, and another amount of the second eigenvalue to the kth power times the second eigenvector, and so on. My conscience always makes me say at least once per lecture that this requires a complete set of eigenvectors. Otherwise, we might not be able to expand u naught in the eigenvectors, and we couldn't get started. But once we're started with u naught when k is 0, then every a brings in these lambdas. And now you can see what the steady state is going to be. If lambda 1 is 1, so lambda 1 equals 1 to the kth power, and these other eigenvalues are smaller than 1. So I've sort of scratched over the equation there we had this term, but what happens to that term if the lambda is smaller than 1? Then as we take powers, as we iterate, as we go forward in time, this goes to 0, right? Can I just, having scratched over it, I might as well scratch further. That term and all the other terms are going to 0 because all the other eigenvalues are smaller than 1. And the steady state that we're approaching is just whatever there was. This is the x1 part of the initial condition u0 is the steady state. This much we know from from what we've already done. So I want to see why. Let's at least see number 1, why 1 is an eigenvalue. And then there's actually, in this chapter, we're interested not only in eigenvalues but also eigenvectors. And there's something special about the eigenvector. Let me write down what that is. The eigenvector x1 is the eigenvector, and all its components are positive. So the steady state is positive, if the start was. If the start was, well, actually, in general, this might have some component 0 always, but no negative components in that eigenvector. Okay, can I come to that point? How can I look at that matrix? So that was just an example. How could I be sure? How can I see that a matrix, if the columns add to 1, if the columns add to 1, this property means that lambda equal 1 is an eigenvalue. Okay, so let's just think that through. What am I saying about, let me look at A, and if I believe that 1 is an eigenvalue, then I should be able to subtract off 1 times the identity, and then I would get a matrix that's what, minus 0.9, minus 0.01, and minus 0.6 when I took the 1s away, and the other parts, of course, are still what they were. And this is still 0.2, and 0.7. And, okay, what's up with this matrix now? I've shifted the matrix, this Markov matrix, by 1, by the identity. And what do I want to prove? What is it that I believe this matrix, about this matrix? I believe it's singular. Singular will, if A minus I is singular, that tells me that 1 is an eigenvalue, right? The eigenvalues are the numbers that I subtract off, the shifts, the numbers that I subtract from the diagonal to make it singular. Now, why is that matrix singular? We could compute its determinant, but we want to see a reason that would work for every Markov matrix, not just this particular random example. So what is it about that matrix? Well, I guess you could look at its columns now. What do they add up to? 0. The columns add to 0. So all columns, let me put all columns now of A minus I add to 0. And then I want to realize that this means A minus I is singular. Okay. Why? So I could, that could be a quiz question, a sort of theoretical quiz question. If I give you a matrix and I tell you all its columns add to 0, give me a reason, because it is true, that the matrix is singular. Okay, I guess actually now I'm thinking of 2 or 3 ways to see that. How would you do it? We don't want to take its determinant somehow. For the matrix to be singular, well, it means that these 3 columns are dependent, right? The determinant will be 0 when those 3 columns are dependent. You see, we're at a point in this course now where we have several ways to look at an idea. We can take the determinant. Here we don't want to. But we met singular before that. Those columns are dependent. So how do I see that those columns are dependent? They all add to 0. Let's see. Well, actually, another thing I know is that I would like to be able to show is that the rows are dependent. Maybe that's easier. If I know that all the columns add to 0, that's my information, how do I see that those 3 rows are linearly dependent? What combination of those rows gives the 0 row? How could I combine those 3 rows, those 3 row vectors, to produce the 0 row vector? And that would tell me those rows are dependent, therefore the columns are dependent, the matrix is singular, the determinant is 0. Well, you see it. I just add the rows. 1 times that row plus 1 times that row plus 1 times that row is the 0 row. The rows are dependent. In a way, that 1, 1, 1, because it's multiplying the rows, is like an eigenvector it's in the left null space, right? 1, 1, 1 is in the left null space. It's singular because the rows are dependent. And can I just keep the reasoning going? Because this vector 1, 1, 1 it's not in the null space of the matrix, but it's in the null space of the transpose, is in the null space of the transpose. And that's good enough. If we have a square matrix, and the rows are dependent, that matrix is singular. So it turned out that the immediate guy we could identify was 1, 1, 1. Of course, there will be somebody in the null space, too. And actually, who will it be? So now I want to ask about the null space of the matrix itself. What combination of the columns gives 0? I don't want to compute it because I just made up this matrix, and it would take me a while. It looks sort of doable because it's 3 by 3. But my point is, what vector is it? Once we found it, what have we got that's in the null space of A? It's the eigenvector, right? That's where we find x1. Then x1, the eigenvector, is in the null space of A. That's the eigenvector corresponding to the eigenvalue 1, right? That's how we find eigenvectors. So those 3 columns must be dependent. Some combination of columns of those 3 columns is the 0 column, and the 3 components in that combination are the eigenvector. And that guy is the steady state. Okay. So I'm happy about the thinking here, but I haven't completed it because I haven't found x1. But it's there. Another thought came to me as I was doing this. Another little comment about eigenvalues and eigenvectors because of A and A transpose. What can you tell me about eigenvalues of A, and eigenvalues of A transpose? Whoops. They're the same. So this is a little comment. It's useful since eigenvalues are generally not easy to find. It's always useful to know some cases where you've got them. And this is, if you know the eigenvalues of A, then you know the eigenvalues of A transpose. Eigenvalues of A transpose are the same. And can I just review why that is? So to find the eigenvalues of A, this would be determinant of A minus lambda I equals 0. That gives me an eigenvalue of A. Now, how can I get A transpose into the picture here? I'll use the fact that the determinant of a matrix and the determinant of its transpose are the same. The determinant of a matrix equals the determinant of the transpose. That was property 10, the very last guy in our determinant list. So I'll transpose that matrix. This leads to this. I just take the matrix and transpose it. But now what do I get when I transpose lambda I? I just get lambda I. So that's all there was to the reasoning. The reasoning is that the eigenvalues of A solve that equation. The determinant of a matrix is the determinant of its transpose. So that gives me this equation, and that tells me that the same lambdas are eigenvalues of A transpose. So that, backing up to the Markov case, 1 is an eigenvalue of A transpose, and we actually found its eigenvector, 1, 1, 1. And that tells us that 1 is also an eigenvalue of A, but of course it has a different eigenvector. The left null space isn't the same as the null space, and we would have to find it. So there's some vector here, which is x1, that produces 0, 0, 0. Actually, it wouldn't be that hard to find. As I'm talking, I'm thinking, OK, am I going to follow through and actually find it? Well, I can tell from this one, look, if I put a 0.6 there and a 0.7 there, then I'll be OK in the last row, right? Now, I only remains to find one guy. And let me take the first row then. Minus 0.54 plus 0.21. There's some big number going in there, right? So I have, just to make the first row come out 0, I'm getting minus 0.54 plus 0.21. So that was minus 0.33. And what do I want? Like 3,300? This is the first time in the history of linear algebra that an eigenvector has ever had a component 3,300. But I guess it's true, because then I multiply by minus 1 over 100. Oh, no, it was 0.33. So is this just, oh, shoot, only 33. OK, only 33. OK, so there's the eigenvector. Oh, and notice that it did turn out, at least, to be all positive. So that was like the theory predicts that part, too. I won't give the proof of that part. So 33.6, 33.7. OK, now those are that's the linear algebra part. Can I get to the applications? Where do these Markov matrices come from? Because that's part of this course and absolutely part of this lecture. OK, so where's an application of Markov matrices? OK. Markov matrices. So my equation, then, that I'm solving and studying is this equation, UK plus 1 equals AUK. And now A is a Markov matrix. A is Markov. And I want to give an example. Can I just create an example? It'll be 2 by 2. And it's one I've used before because it seems to me to bring out the idea. It's because we have 2 by 2, we have 2 states, let's say California and Massachusetts. And I'm looking at the populations in those 2 states, the people in those 2 states, California and Massachusetts. And my matrix A is going to tell me in a year, some movement has happened. Some people stayed in Massachusetts. Some people moved to California. Some smart people moved from California to Massachusetts. Some people stayed in California and made $1 billion. OK, so there's a matrix there with 4 entries. And those tell me the fractions of my population. So I'm going to use fractions. So they won't be negative, of course, because only positive people are involved here. And they'll add up to 1 because I'm accounting for all people. So that's why I have these 2 key properties. The entries are greater or equal 0 because I'm looking at probabilities. Do they move? Do they stay? Those probabilities are all between 0 and 1. And the probabilities add to 1 because everybody's accounted for. I'm not losing anybody, gaining anybody in this Markov chain. It conserves the total population. OK, so what would be a typical matrix then? So this would be U, California, and U, Massachusetts, at time t equal k plus 1. And it's some matrix, which we'll think of, times U, California, and U, Massachusetts, at time k. And notice this matrix is going to stay the same, forever. So that's a severe limitation on the example. The example has the same Markov matrix, the same probabilities act at every time. OK, so what's a reasonable say? Say 0.9 of the people in California at time k stay there. And 0.1 of the people in California move to Massachusetts. Notice why that column added to 1. Because we've now accounted for all the people in California at time k. 9/10 of them are still in California. 1/10 are here at time k plus 1. OK, what about the people who are in Massachusetts? This is going to multiply column 2, right? By our fundamental rule of multiplying matrix by vector. It's the population in Massachusetts. Shall we say that after the Red Sox fail again, only 80% of the people in Massachusetts stay, and 20% move to California. Okay. So again, this adds to 1, which accounts for all people in Massachusetts where they are. So there is a Markov matrix. Non-negative entries adding to 1. What's the steady state? If everybody started in Massachusetts, say at, when the Pilgrims showed up or something, then where are they now? Where are they at time 100, let's say? Or maybe, I don't know how many years since the Pilgrims, 300 and something? Or, and actually, where will they be, like, way out 1 million years from now? I could multiply, take the powers of this matrix. In fact, you ought to be able to figure out what is the 100th power of that matrix. Why don't we do that? But let me follow the steady state. So what's my starting? My starting UCal, UMass at time 0 is, shall we say, shall we put anybody in California? Let's make 0 there. And say the population of Massachusetts is, let's say, 1,000 just then. Okay. So the population is, so the populations are 0 and 1,000 at the start. What can you tell me about this population after k steps? What will UCal plus UMass add to? 1,000. Those 1,000 people are always accounted for. But, so UMass will start dropping from 1,000. UCal will start growing. Actually, we could see, why don't we figure out what it is after 1? After 1 time step, what are the populations? At time 1. So what happens in 1 step? You multiply once by that matrix, and let's see, 0 times this column, so it's just 1,000 times this column, so I think we're getting 200 and 800. So after the first step, 200 people are in California. Now at the following step, I'll multiply again by this matrix. More people will move to California. Some people will move back. 20 people will come back. And the net result will be that the California population will be above 200 and the Massachusetts below 800, and they'll still add up to 1,000. Okay, I do that a few times. I do that 100 times. What's the population? Well, okay, to answer any question like that, I need the eigenvalues and eigenvectors, right? As soon as I've created an example, but as soon as I want to solve anything, I have to find eigenvalues and eigenvectors of that matrix. Okay, so let's do it. So there's the matrix 0.9, 0.2, 0.1, 0.8, and tell me its eigenvalues. Lambda equals, so tell me one eigenvalue. 1, thanks. And tell me the other one. What's the other eigenvalue? From the trace or the determinant, from the trace is what is like easier. So the trace of that matrix is 1.7. So the other eigenvalue is 0.7. And notice that it's less than 1. And notice that the determinant is 0.72 minus 0.02, which is 0.7. Right. Okay, now to find the eigenvectors. So that's lambda 1. And the eigenvector, I'll subtract 1 from the diagonal, right? So can I do that in light here? Subtract 1 from the diagonal, have minus 0.1 and minus 0.2. And of course, these are still there. And I'm looking for its, this is going to be x1. It's the null space of A minus I. Okay, everybody sees that it's 2 and 1. Okay? And now how about, notice that that eigenvector is positive. And actually, we can jump to infinity right now. what's the population at infinity? It's a multiple. This eigenvector is giving the steady state. It's some multiple of this, and how is that multiple decided? By adding up to 1,000 people. So the steady state, the C1x1, this is the x1, but that adds up to 3. So I really want it's going to be 2/3 of 1,000 and 1/3 of 1,000, making a total of the 1,000 people. That'll be the steady state. That's really all I need to know at infinity. But if I want to know what's happened after just a finite number like 100 steps, I better find this eigenvector. So can I look at, I'll subtract 0.7 from the diagonal, and I'll get that. And I'll look at the null space of that one. And this is going to give me x2 now, and what is it? So what's in the null space? That's certainly singular, so I know my calculation is right. And 1 and minus 1. 1 and minus 1. So I'm prepared now to write down the solution after 100 time steps, the populations after 100 time steps, right? Can we remember the 0.1, the 1 with this 2, 1 eigenvector, and the 0.7 with the minus 1, 1 eigenvector? So I'll just write it above here. U after k steps is some multiple of 1 to the k times the 2, 1 eigenvector, and some multiple of 0.7 to the k times the minus 1, 1 eigenvector. Right? This is how powers of a matrix work. When I apply those powers to a U0, so it's U0, which was 0, 1,000. That has to be correct at k equals 0. So I'm plugging in k equals 0, and I get C1 times 2, 1, and C2 times minus 1, 1. 2 equations, 2 constants, certainly independent eigenvectors. So there's a solution, and do you see what it is? Let's see, I guess we already figured that C1 was 1,000 over 3, I think. Did we think that had to be 1,000 over 3? And maybe C2 would be, excuse me, get an eraser. We can, I think we'd get it here. C2, we want to get a 0 here. So maybe we need plus 2,000 over 3. I think that has to work. 2 times 1,000 over 3 minus 2,000 over 3, that'll give us the 0. And the 1,000 over 3 and the 2,000 over 3 will give us 3,000 over 3, the 1,000. So this is what we approach this part with the 0.7 to the kth power is the part that's disappearing. Okay, that's Markov matrices. That's an example of where they come from modeling movement of people with no gain or loss, with total count conserved. Okay, I just, if I can add one more comment, because you'll see Markov matrices in electrical engineering courses, and often you'll see them, so here's my little comment. Sometimes in a lot of applications they prefer to work with row vectors. So they, instead of, this was natural for us, right, for all the eigenvectors to be column vectors. So our columns added to 1 in the Markov matrix. Just so you don't think, well, what's going on? If we work with row vectors and we multiply vector times matrix, so we're multiplying from the left, then it'll be then we'll be using the transpose of this matrix, and it'll be the rows that add to 1. So in other textbooks, you'll see instead of columns adding to 1, you'll see rows add to 1. Okay, fine. Okay, that's what I wanted to say about Markov. Now I want to say something about projections and even leading in a little into Fourier series. Because, but before any Fourier stuff, let me make a comment about projections. So this is a comment about projections onto with an orthonormal basis. So, of course, the basis vectors are q1 up to qn. Okay. I have a vector b. Let me imagine this is a basis. Let's say I'm in n by n. I've got n orthonormal vectors. I'm in n-dimensional space, so they're a basis. Any vector v could be expanded in this basis. So any vector v is some combination, some amount of q1 plus some amount of q2 plus some amount of qn. So any v. I just want you to tell me what those amounts are. What are x1? What's x1, for example? So I'm looking for the expansion. This is really a projection. I could really use the word expansion. I'm expanding the vector in the basis. And the special thing about the basis is that it's orthonormal. So that should give me a special formula for the answer, for the coefficients. So how do I get x1? What's a formula for x1? I can go through the projection, the Q transpose Q, all that normal equations, and I'll come out with this nice answer that I think I can see right away. How can I get a hold of x1 and get these other x's out of the equation? So how can I get a nice, simple formula for x1? And then we want to see, sure, we knew that all the time. Okay, so what's x1? The good way is take the inner product of everything with q1. Take the inner product of that whole equation, every term, with q1. What will happen to that last term? The inner product, if I take the dot product with q1, I get 0, right? Because this basis was orthonormal. If I take the dot product with q2, I get 0. If I take the dot product with q1, I get 1. So that tells me what x1 is. q1 transpose v, that's taking the dot product, is x1 times q1 transpose q1 plus a bunch of zeros. And this is a 1, so I can forget that. I get x1 immediately. So you see what I'm saying is that if I have an orthonormal basis, then the coefficient that I need for each basis vector is a cinch to find. Let me just, I have to put this into matrix language too, so you see it there also. If I write that first equation in matrix language, what is it? I'm writing in matrix language, this equation says, I'm taking these columns. Are you guys good at this now? I'm taking those columns times the x's and getting v, right? That's the matrix form. Okay, that's the matrix Q. Q, x is v. What's the solution to that equation? Of course, it's x equal Q inverse v. So x is Q inverse v, but what's the point? Q inverse in this case is simple. I don't have to work to invert this matrix Q because of the fact that these columns are orthonormal. I know the inverse to that, and it is Q transpose. when you see a Q, a square matrix with that letter Q, that just triggers Q inverse is the same as Q transpose. So the first component then, the first component of X is the first row times V. And what's that? The first component of this answer is the first row of Q transpose. That's just Q1 transpose times V. So that's what we concluded here too. Okay. So nothing Fourier here. The key ingredient here was that the Q's are orthonormal. And now that's what Fourier series are built on. So now in the remaining time, let me say something about Fourier series. Okay. So Fourier series is, well, we've got functions. We've got a function f of x. And we want to write it as a combination of, maybe it has a constant term. And then it has some cosine x in it. And it has some sine x in it. And it has some cosine 2x in it. And some sine 2x, and forever. So what's the difference between this type problem and the one above it? This one's infinite. But the key property of things being orthogonal is still true for sines and cosines. So it's the property that makes Fourier series work. So that's called a Fourier series. Better write his name up. Fourier series. So it was Joseph Fourier who realized that, hey, I could work in function space. Instead of a vector v, I could have a function f of x. Instead of orthogonal vectors, q1, q2, q3, I could have orthogonal functions, the constant, the cosine x, the sine x, the cos 2x, but infinitely many of them. I need infinitely many because my space is infinite dimensional. So this is like the moment in which we leave finite dimensional vector spaces and go to infinite dimensional vector spaces. And our basis, so the vectors are now functions. And of course, there are so many functions that we've got an infinite dimensional space. And the basis vectors are functions too. A naught, the constant function 1. So my basis is 1 cos x, sine x, cos 2x, sine 2x, and so on. And the reason Fourier series is a success is that those are orthogonal. Okay, now what do I mean by orthogonal? I know what it means for two vectors to be orthogonal. Y transpose x equals 0, right? Dot product equals 0. But what's the dot product of functions? I'm claiming that whatever it is, the dot product, or we would more likely use the word inner product, of, say, cos x with sine x is 0. And cos x with cos 2x, also 0. So let me tell you what I mean by that dot product. Well, how do I compute a dot product? So let's just remember, for vectors, v transpose w. For vectors, so this was vectors, v transpose w was v1 w1 plus vn wn. Okay, now functions. Now I have two functions, let's call them f and g. What's with them now? The vectors had n components, but the functions have a whole, like, continuum. To graph the function, I just don't have n points. I've got this whole graph. So I have functions. I'm really trying to ask you, what's the inner product of this function f with another function g? And I want to make it parallel to this the best I can. So the best parallel is to multiply f of x times g of x at every x. And here I just had n multiplications, but here I'm going to have it a whole range of x's. And here I added the results. What do I do here? So what's the analog of addition when you're in a continuum? It's integration. So that the dot product of two functions will be the integral of those functions dx. Now I have to say, well, what are the limits of integration? And for this Fourier series, this function f of x, if I'm going to have, if that right-hand side is going to be f of x, that function that I'm seeing on the right, all those sines and cosines, they're all periodic with period 2 pi. So that's what f of x had better be. So I'll integrate from 0 to 2 pi. Everything is on the interval 0, 2 pi now. Because if I'm going to use these sines and cosines, then f of x is equal to f of x plus 2 pi. This is periodic. Periodic functions. Okay. So now I know what... I've got all the right words now. I've got a vector space, but the vectors are functions. I've got inner products, and the inner product gives a number, all right. It just happens to be an integral instead of a sum. Then I have the idea of orthogonality, because actually, let's just check orthogonality. If I take the integral, let me do sine x times cos x, sine x times cos x dx from 0 to 2 pi, I think we get 0. That's the differential of that, so it would be 1/2 sine x squared. Was that right? Between 0 and 2 pi. And, of course, we get 0. And the same would be true with a little more, some trig identities to help us out, of every other pair. So we have now an orthonormal infinite basis for function space. And all we want to do is express a function in that basis. And so the end of my lecture is, OK, what is A1? What's the coefficient? How much cosine x is there in a function compared to the other harmonics? How much constant is in that function? That would be an easy question. The answer, A0, will come out to be the average value of f. That's the amount of the constant that's in there, its average value. But let's take A1 as more typical. How will I get, here's the end of the lecture then, how do I get A1? The first Fourier coefficient. OK. I do just as I did in the vector case. I take the inner product of everything with cos x. Take the inner product of everything with cos x. Then on the left, I have the inner product is the integral of f of x times cos x dx. And on the right, what do I have? When I say take the inner product with cos x, let me put it in ordinary calculus words. Multiply by cosine x and integrate. That's what inner products are. So if I multiply that whole thing by cos x and I integrate, I get a whole lot of zeros. The only thing that survives is that term. All the others disappear. And that term is A1 times the integral of cos x squared dx, 0 to 2 pi, equals, so this was the left side, and this is all that's left on the right-hand side. And this is not 0, of course, because it's the length of the function squared. It's the inner product with itself. And a simple calculation gives that answer to be pi. So that's an easy integral, and it turns out to be pi, so that A1 is 1 over pi times this integral. So there is actually, that's Euler's famous formula for the, or maybe Fourier found it, for the coefficients in a Fourier series. And you see that it's exactly an expansion in an orthonormal basis. Okay, thanks. So I'll do a quiz review on Monday, and then the quiz itself in Walker on Wednesday. Okay, see you Monday. Thanks.